somewhere above the atmosphere, far past the reach of weather or clouds. A golden mirror, the width of a tennis court, is drifting slowly around a point in space, gathering light that has been traveling toward it for longer than there have been eyes anywhere to see it. It is not doing anything dramatic. It is simply looking patiently, the way a very old and very careful observer looks. And in that patient looking, it has begun to notice something quietly strange about the universe. We thought we understood. This is a story about that strangeness, not a story about disaster or about some grand mistake unraveling everything scientists have built. It is closer to the feeling of rereading a familiar book and noticing, for the first time, a paragraph that does not quite fit with the rest. The paragraph does not undo the book. It just means there is more to understand than anyone realized, and that the people who study these things are, at this very moment, in the middle of figuring out why, to tell it properly, we should start somewhere calm and simple, with a single number that almost nobody outside of astronomy thinks about very often, and yet which quietly underpins our entire picture of how old the universe is, how big it is, and how it began. That number describes how fast the universe is expanding, not expanding into anything exactly, since there does not seem to be an edge or an outside for it to expand into. It is more that the space between things is stretching, gently and continuously, everywhere at once. Two galaxies sitting far apart from each other are drifting apart not because they are moving through space towards some destination, but because the space between them is itself growing. If you find that a little difficult to picture, an old and gentle way of imagining it is to think of raisins scattered through a lump of bread dough before it goes into the oven. As the dough rises, every raisin moves away from every other raisin, not because any of them are actively traveling, but because the dough itself is swelling in every direction at once. From the point of view of any single raisin, it would look as though all the other raisins were retreating from it. There is no special center, no raisin that stays still while the others flee. It is simply the dough itself, expanding. The universe behaves something like that, on a scale so much larger that comparing it to a loaf of bread almost feels a little absurd, and yet the basic intuition holds up remarkably well. Space itself is stretching, and as it stretches, the galaxies embedded within it drift apart from one another. The number that describes how quickly this stretching is happening today, right now, is named after the astronomer who first tried to measure it in a serious way. Back in the 1920s, his name was Edwin Hubble, and working at an observatory in the mountains above Los Angeles, using a telescope that would be considered almost quaint by today's standards, he noticed something that had not been appreciated before. The more distant a galaxy appeared to be, the faster it seemed to be rushing away from us. Not just some galaxies, all of them, in every direction, with the most distant ones retreating the fastest. This was already a strange enough discovery on its own. It suggested, gently but unmistakably, that the universe was not a fixed, static backdrop the way people had assumed for centuries. It was expanding, and if you ran that expansion backward in your mind, like rewinding a film, everything would eventually converge to a single, incredibly dense point. It was the first real observational thread pointing toward what we would later call the Big Bang. But Hubble's original number for the expansion rate was quite far from what we now believe to be correct. In fact, it was off by such a wide margin that if you took it completely at face value and used it to calculate the age of the universe, you would end up with a universe younger than the Earth sitting inside it, which is obviously not possible. Something in the early measurement was miscalibrated. It would take decades of careful, unglamorous work by many astronomers, refining instruments, correcting for subtle sources of error. and slowly nudging the number towards something more trustworthy. For much of the 20th century, this refinement turned into an unusually personal and occasionally quite heated disagreement among astronomers. Two rival groups, using different techniques and different assumptions, arrived at answers that differed from each other by close to a factor of 2. One camp insisted the true expansion rate was close to 50 in the standard units astronomers use for this measurement. The other camp was equally convinced it was closer to 100. For a number that both sides agreed only one answer could be correct. A disagreement of that size split the field for the better part of 30 years, with each side publishing papers, defending methods, and occasionally speaking about the other camp's conclusions in less than diplomatic terms. It is worth pausing on this, because it tells you something reassuring about how science actually works. In contrast to how it sometimes gets portrayed, it is not a smooth, orderly march where each measurement builds neatly on the last. It is often messy, contentious, and slow, with brilliant people looking at the same sky and arriving at genuinely different conclusions, sometimes for years at a stretch, until better instruments or cleverer methods finally settle the matter. By the early years of this century, that old feud finally seemed to be resolved. A large, careful project using the original Hubble Space Telescope, named in honor of the same astronomer who had started this whole conversation decades earlier, combined multiple independent techniques and converged on a value close to 70 in those same standard units. The margin between the two old camps closed. Astronomers, by and large, felt they had finally nailed down this stubborn number after the better part of a century of effort. Except that, as often happens in careful science, greater precision did not bring simplicity. It brought a new, smaller, far more stubborn puzzle to replace the old one. There are, it turns out, two genuinely different ways to measure how fast the universe is expanding today, and they approach the question from opposite ends of cosmic history. The first method looks backward, almost all the way to the beginning of everything, when the universe was extremely young, only a few 100,000 years old. It was filled with a hot, dense fog of charged particles, so thick with electrons that light itself could not travel freely through it. Photons would be emitted and almost immediately scattered by a nearby electron, over and over, unable to escape in a straight line. The whole universe, in a sense, was opaque, the way the inside of a thick cloud is opaque even in daylight. Then, as the universe expanded and cooled, something changed. The temperature dropped low enough that electrons could finally settle into orbits around atomic nuclei, forming stable, neutral atoms for the first time. Once that happened, there were far fewer free electrons around to scatter light, and photons could suddenly travel in straight lines, uninterrupted, for the rest of time. The universe became transparent almost overnight. In cosmic terms, the light that was released at that exact moment is still traveling through space today, stretched by the expansion of the universe into faint microwave radiation, arriving from every direction in the sky. It is often called the afterglow of the Big Bang, and it is, in a very real sense, a baby picture of the universe, taken when it was only about 380,000 years old. A satellite named after the physicist Max Planck spent years mapping this ancient afterglow with extraordinary precision, charting tiny variations in its temperature from one patch of sky to another. Variations smaller than a millionth of a degree. Those tiny variations are not noise. They are the fingerprints of sound waves that rippled through the hot plasma of the infant universe. And their exact pattern encodes an enormous amount of information about the contents and behavior of the cosmos at that early time. Physicists take that information, feed it into a mathematical framework, often called the Standard Model of Cosmology, and let the equations run forward across nearly 14 billion years of cosmic history, all the way to today. Out the other end comes a prediction for how fast the universe should be expanding right now in the present day. That predicted value comes out to about 67 kilometers per second per megaparsec, which is the somewhat unwieldy unit astronomers use for this measurement. It roughly describes how much faster a galaxy appears to be receding from us, for every additional unit of distance separating us from it. The important thing is not the unit itself, but the number 60, and the fact that it comes with a remarkably small margin of error. The second method throws out the idea of modeling the beginning of the universe entirely. Instead, it simply measures the expansion directly. In the present day, by carefully building what astronomers call a distance ladder, the foundation of that ladder rests on a particular kind of star, discovered in an unusual way more than a century ago by an astronomer named Henrietta Leavitt, who was working at the Harvard College Observatory at a time when women were rarely given the chance to do original research in the field. Leavitt was studying photographic plates of a certain class of pulsing stars, stars that rhythmically swell and shrink, brightening and dimming over the course of days or weeks. What she noticed was remarkable. The longer a star took to complete one full pulse, the intrinsically brighter that star actually was. It was not a loose correlation. It was a precise, dependable relationship, one that meant if you simply timed how long a star took to pulse, you could work out exactly how bright it truly was. Regardless of how far away it happened to be, that discovery turned out to be one of the most quietly important measurements in the history of astronomy, because it handed scientists a reliable way to measure distances across the universe. If you know how intrinsically bright a star actually is, and you measure how dim it appears from Earth, the difference between those two numbers tells you exactly how far its light has had to travel. These pulsing stars became, in effect, cosmic lighthouses, each one broadcasting both its brightness and, indirectly, its distance. From these nearby lighthouses, astronomers climb outward to galaxies that host the same pulsing stars, and within those same galaxies, they also find a different kind of star, one that does not pulse gently but instead ends its life in a sudden, brilliant explosion. These exploding stars belong to a family that detonates with almost exactly the same intrinsic brightness every time, no matter where in the universe they occur. Because their true brightness is so consistent, their apparent faintness in our telescopes becomes another kind of ruler, one that can be laid out across distances far greater than the pulsing stars alone could ever reach, hundreds of millions or even billions of light years away. Each rung of this ladder is calibrated against the one below it, the pulsing stars anchoring the exploding stars, and the exploding stars extending the reach outward into the depths of the universe. The way a surveyor might first carefully measure a valley floor before using that measurement to work out the height of a distant mountain range by triangulation, a physicist named Adam Rees, working with a large team of collaborators, spent years refining this exact technique, gradually building what is widely regarded as one of the most careful and thoroughly cross-checked measurements in modern astronomy. When their ladder was fully built and their calculations run, the number they arrived at for the expansion rate of the universe today was not 60, it was 73.6. In those same units, a difference of 6 or 7 units might not sound dramatic on its own, but in a field where the best measurements are routinely accurate to within a single percent, a gap of 8 or 9% between two careful, independent methods is not something you can shrug off as noise. It is closer to a genuine disagreement between two different pictures of reality, both supported by rigorous, painstaking measurement. It is worth sitting with what that disagreement actually means, because it is easy to hear two numbers that are reasonably close to each other, 67 and 73.6, and assume the stakes must be fairly small. They are not. If the universe is genuinely expanding faster today than the early universe model predicts it should be, then almost everything built on top of that model shifts along with it. The calculated age of the universe changes. The size of the observable universe changes. The timeline for when the very first stars switched on, when the first generation of heavy elements were forged inside the cores of dying stars, when the raw materials for planets and chemistry and eventually biology first became available. All of it moves, sometimes by hundreds of millions of years in either direction. This is not a matter of nudging one small dial on an instrument panel. It touches the entire timeline of everything that has ever existed. For a long stretch of time after this discrepancy first became clear, most astronomers assumed it would eventually resolve itself, the way most such disagreements in science quietly do, through the discovery of some overlooked technical error. The leading suspect for years was a subtle effect called crowding. The pulsing stars that anchor the bottom of the distance ladder tend to live inside the busy, dust-filled spiral arms of galaxies, regions crowded with other stars, gas, and glowing dust. Older telescopes, with less sharp vision, sometimes struggled to fully separate the light of one individual pulsing star from its crowded neighbors, blending them together into a single blurred point of light. A star that looks blurred together with its neighbors can appear artificially brighter than it truly is on its own, and a star that looks brighter than it really is will appear closer than it actually is. Since brightness and distance are so tightly linked in this kind of measurement, a star that appears closer than it truly is will, in turn, make the whole expansion rate calculated from it appear faster than it should. Clean up that blurring, the reasoning went, and the inflated distances would shrink back down, and the tension between the two numbers would quietly relax. This is where the newest and most capable telescope ever built enters the story. Sitting roughly 1.5 million kilometers from Earth, far beyond the warmth and haze of our own atmosphere, is an observatory with a 6.5-meter mirror plated in gold, built specifically to gather infrared light with a sensitivity that dwarfs anything that came before it. If any instrument in existence could see cleanly through the crowding problem and settle the disagreement once and for all, this was the one. Many astronomers genuinely expected this new telescope to gently resolve the whole controversy, revealing the blurring, correcting the distances downward, and pulling the higher number back toward the lower one. Some were, by their own admission, quietly preparing to treat the disagreement as a closed chapter even before the new data had fully arrived. That is not what happened. When Rees and his collaborators pointed the new telescope at exactly the stars in question, using its much sharper vision to separate individual stars from their crowded surroundings, the measurements held. The distances did not shrink. The expansion rate calculated from them stayed almost exactly where it had been before, close to 73.5. Across a major study spanning the telescope's first 2 years of operation, the team measured these distances in 3 separate, independent ways, cross-checking different categories of stars against one another, and all 3 approaches arrived at essentially the same place. The possibility of simple measurement error, the kind that might have quietly resolved the whole affair, could be ruled out with a very high degree of confidence. In Rees's own account of the result, what remained afterward was what he called the real and genuinely interesting possibility that our current understanding of the universe is in some way incomplete. There is a small anecdote from a physics conference in California some years earlier that has stuck with many people in the field. Rees had asked another physicist, a Nobel laureate named David Gross, whether the community should start referring to this stubborn disagreement as a problem. Gross's response was blunt. Do not call it attention, he said. Do not even call it a problem. Call it a crisis. That word, crisis, is a strong one, and it is worth noting that plenty of careful scientists would push back on it. But it captures something true about how seriously the field has come to take this disagreement, and it has led to a number of genuinely creative attempts to explain where the extra speed might be coming from. One of the more promising ideas is called early dark energy. To understand it, it helps to remember that dark energy, in general, is the name physicists give to whatever mysterious property of empty space is causing the universe's expansion to accelerate rather than slow down. Early dark energy proposes something more specific and more temporary, a brief, short-lived burst of that same repulsive push, occurring in the first few 100,000 years after the Big Bang, which then faded away almost as quickly as it appeared. If something like that truly happened, it would not need to change anything about the universe today. Its effect would have been felt only in that brief early window, subtly altering the physical conditions that the cosmic microwave background afterglow was later imprinted with. That, in turn, would shift the prediction that today's Standard Model of Cosmology extrapolates forward from that early light, nudging the predicted expansion rate upward, closer to the value found by the distance ladder, without requiring any change to the well-tested physics that governs the rest of cosmic history. One physicist working on this idea described it, in a memorable phrase, as though the newborn universe had received a single, unexpected kick right at the moment of its birth, a kick that rippled forward silently across 14 billion years and slightly altered the number we measure today. It is an elegant idea. Nobody has directly detected this early burst of energy. No one has proven that it existed. But among the various proposed solutions to this disagreement, it remains one of the very few that could resolve the tension without requiring the rest of the Standard Model to be torn down and rebuilt from scratch. And yet, not everyone in the field is convinced there is a genuine crisis to resolve in the first place. An astronomer named Wendy Friedman has spent much of her career building an independent version of the same distance ladder, one that deliberately avoids the pulsing stars that anchor Reese's approach. Instead, her method leans on a different category of aging stars, ones found in the calmer, far less crowded outer regions of galaxies, well away from the busy, dust-choked spiral arms where crowding is most likely to cause trouble. When Friedman turned the same new telescope on her own chosen set of target stars, her team's 3 independent methods converged on a value close to 70, a number sitting almost precisely in the no man's land between the two competing camps. Her own conclusion, stated plainly, was the opposite of a crisis. Based on this new data, she reported, there is no strong evidence for a genuine disagreement between the early and late universe measurements. If anything, she suggested, the Standard Model of Cosmology appears to be holding up rather well. Friedman is not a fringe figure making an easily dismissed claim. She is among the most decorated astronomers working today, having received one of the highest scientific honors her country awards. And so this has become one of the most closely watched good faith disagreements in modern physics. 2 exceptionally careful research teams, using the same class of telescope, pointed at the same sky, arriving at meaningfully different conclusions about what that sky is actually telling them. It is a useful reminder that even at the very frontier of precision measurement, interpreting data well is every bit as difficult as gathering it in the first place. It is worth taking a short detour here, back to an earlier moment in the history of cosmology, because this is not actually the first time the field has found itself facing what looked, on the surface, like an outright contradiction. In the 1990s, astronomers ran into a genuinely uncomfortable problem. Careful measurements of the ages of the oldest stars in our galaxy, found in dense, ancient clusters, suggested those stars were older than the calculated age of the universe itself. That is, on its face, a logical impossibility. A container cannot be younger than the things sitting inside it. Something in the reasoning had to be wrong, and for a while, nobody was quite sure what. The resolution came from an entirely unexpected direction. Two separate teams of astronomers, working independently and initially in friendly competition with one another, were using distant exploding stars, the same type used in the modern distance ladder, to measure how the expansion of the universe had changed over cosmic time. The expectation, shared by nearly everyone at the time, was that the mutual gravity of all the matter in the universe should be gradually slowing that expansion down, the way gravity slows a ball thrown upward before eventually pulling it back down. Instead, both teams found the opposite. The expansion of the universe was not slowing down. It was speeding up. Something was actively pushing galaxies apart, faster and faster, working against the pull of gravity rather than being reined in by it. This mysterious pushing force needed a name, and physicists settled on dark energy, an admittedly vague label for something whose fundamental nature is still not understood, even now, decades later. The scientists who led this discovery were awarded a Nobel Prize in physics in 2011 for the finding. Once dark energy entered the picture, the earlier puzzle about ancient stars being older than the universe dissolved almost immediately. An accelerating expansion meant the universe had been expanding more slowly in its earlier history than a simple, decelerating model would have suggested, which meant more total time had passed since the Big Bang than the old calculations allowed. The oldest stars were, after all, comfortably younger than the universe containing them. What had looked like a fatal contradiction turned out to be the shadow of something enormous that nobody had previously imagined. An entire new component of the universe hiding in plain sight, revealed only because the old numbers refused to add up cleanly. That history matters here, because it establishes a pattern worth remembering. In cosmology, an uncomfortable contradiction between two careful measurements has, at least once before, turned out to be the doorway to a genuinely new piece of physics, rather than evidence that anyone had simply made a mistake. Whether the modern disagreement over the universe's expansion rate will follow the same path remains an open question. But the precedent is there, and it tends to make working cosmologists somewhat more patient with the current puzzle than an outside observer might expect. There is also a newer, more speculative idea circulating alongside early dark energy, one that takes a rather different approach to explaining the disagreement. It proposes that faint magnetic fields, present in the universe from its very earliest moments, might have subtly altered the physics of that ancient afterglow of light, shifting the values that scientists read from it today. This idea is genuinely new, published only in the past couple of years, and it carries the added appeal of potentially solving a second, entirely separate mystery at the same time. The puzzle of where the magnetic fields we observe threading galaxies and the space between them actually came from in the first place. It remains speculative, and the researchers who proposed it are careful to describe it as one candidate explanation among several rather than a settled answer. But it illustrates just how many different directions physicists are currently exploring in the search for a resolution. The disagreement over the universe's expansion rate would be enough on its own to occupy cosmologists for years, but it is not the only puzzle this new telescope has turned up. Almost from the moment it began its observations, it produced a second, quite different kind of surprise, this time involving galaxies rather than expansion rates. When astronomers pointed the telescope toward some of the oldest, faintest light it is capable of gathering, light that has been traveling for the vast majority of the universe's history, They expected to find small, dim, still-forming galaxies, scattered and disorganized. The kind of early structures the Standard Model of Cosmology predicts should exist so soon after the Big Bang. What they found, in some cases, was quite different. They found galaxies that appeared substantially more massive than anyone had anticipated for that early period, some of them rivaling the mass of our own galaxy, observed as they existed only around 500 to 700 million years after the beginning of the universe. To appreciate why that is unusual, it helps to know that our own galaxy took something like 13 billion years to assemble into its current form. Some of these newly observed early galaxies appeared to have reached a comparable mass in a small fraction of that time, well under 1 billion years. When astronomers worked through the physics of how quickly a galaxy could plausibly grow that large, that quickly, the most extreme examples pressed right up against the theoretical limit of what the Standard Model allows. To reach that mass in that amount of time, nearly every available scrap of surrounding gas would have needed to convert directly into stars, with almost none of it lost to heat, or blown away by stellar winds, or left over unused the way it normally is. In a typical galaxy, that conversion efficiency, the fraction of available gas that actually turns into stars, tends to hover around 10%. These early galaxies looked, on first analysis, as though they were operating at something close to 100% efficiency, essentially wasting nothing. That is not how star formation is understood to work in any model astronomers have built. The initial reaction among many researchers was, understandably, some genuine alarm. Then came the quieter, more careful follow-up work that tends to characterize science at its best. The kind of correction that rarely makes headlines, but that matters enormously. A team of astronomers went back through the data and discovered that a meaningful fraction of these apparently overweight galaxies were being distorted by an entirely different phenomenon, one involving black holes rather than stars. At the center of these particular galaxies sat compact, intensely red objects, which turned out to be supermassive black holes actively feeding on surrounding gas. As matter spirals inward toward a black hole, friction heats it to enormous temperatures, and it glows brilliantly, sometimes bright enough to rival or even outshine the combined starlight of the entire galaxy around it. From billions of light years away, viewed through even the sharpest telescope, a galaxy hosting one of these actively feeding black holes can look remarkably similar to a galaxy containing many times more stars than it actually does, because the telescope is fundamentally measuring brightness, and brightness is normally, though not always, a reliable stand-in for mass. Once these black hole imposters were carefully identified and removed from the sample, the majority of the remaining galaxies settled back within the range the Standard Model comfortably predicts. One of the researchers leading this follow-up work stated plainly that there is no crisis in the Standard Cosmological Model, at least not one caused by these particular galaxies. But the story did not close quite as cleanly as that. Reassurance might suggest, even after every identifiable black hole imposter had been carefully stripped out of the sample, astronomers were still left with roughly twice as many genuinely massive early galaxies as the Standard Model comfortably expects to find at that stage in cosmic history. Not enough of a surplus to break the model outright, but enough to bend it, to suggest that something about the early stages of galaxy formation is proceeding a little more efficiently, or a little more quickly than current theory fully accounts for. And the strangeness did not stop there. In a separate observation, astronomers identified a large, fully formed spiral galaxy, one that researchers affectionately nicknamed the Big Wheel, existing within roughly the first couple of billion years of cosmic history. This was notable because spiral structure, the kind of elegant, orderly, rotating disk found in galaxies like our own, is generally thought to take a very long time to develop. A young universe, still turbulent and violent from its own formation, is not usually considered a calm enough environment for such an orderly structure to settle into place so quickly. The big wheel appeared to have managed it anyway. What makes this even more puzzling is that the early universe did not seem to specialize in producing calm, orderly galaxies like the big wheel. A separate team of researchers studied more than 250 galaxies from that same broad era of cosmic history and found essentially the opposite pattern. The overwhelming majority of them were chaotic, turbulent, clumpy structures, still visibly in the process of settling into any kind of stable shape. Nothing like a smooth, orderly spinning disk, so the infant universe, it seems, somehow held both possibilities at once. Messy, adolescent galaxies still searching for their eventual shape, existing side by side in the same narrow slice of cosmic time, with at least one fully grown, elegantly organized spiral that seemingly skipped ahead of schedule. That is not a contradiction the Standard Model handles with any particular grace, and it remains an open area of active research. There is a further layer to this puzzle involving the shapes of these young galaxies. More generally, a study drawing on researchers from a number of different countries examined the overall shapes of many of these early galaxies and found that a surprisingly large number of them were not the tidy spheres or flattened disks that current theory predicts should be common. Instead, they appeared stretched out and elongated, sometimes described informally as cigar-shaped. These elongated shapes do not sit comfortably with the predictions of what is called cold dark matter, the invisible form of matter that current cosmological theory treats as the underlying scaffolding for how all galaxies form and cluster together. Instead, these shapes align somewhat better with predictions from a different, less mainstream family of ideas, involving forms of dark matter that behave in warmer, lighter, more wave-like ways. Ideas that most cosmologists had not previously taken very seriously as competitors to the standard picture. It is worth being careful here, since this remains a genuinely contested area with a great deal of ongoing debate, and no consensus yet exists about whether these unusual shapes truly demand a change to our understanding of dark matter, or whether some other explanation, perhaps involving how these young, distant galaxies are observed and measured, will eventually account for them instead. Dark matter is not simply one ingredient sitting alongside a handful of others in the Standard Model. It functions as the underlying framework of the entire theory, the invisible material whose gravity is thought to have pulled ordinary matter together into galaxies and clusters of galaxies in the first place, shaping how those structures are distributed across billions of light-years of space. If the true nature of dark matter turns out to be even slightly different from what has been assumed for the past several decades, the consequences would ripple through nearly every prediction cosmology currently makes, in something like the way that quietly swapping out the foundation of a building would eventually be felt in every wall built on top of it, even if the change was not obvious at first glance. If you step back and take stock of everything gathered so far, the picture that emerges is one of genuine, accumulating tension rather than a single, isolated anomaly. The disagreement over the universe's expansion rate has refused to resolve itself through simple measurement error. The early universe appears to be producing galaxies that are, in some cases, too large, too structured, and too quickly formed for current theory to comfortably explain. And the underlying nature of dark matter itself, believed to make up more than a quarter of everything that exists, may not behave in quite the way the Standard Model has assumed for the last 25 years. There is even a second, quieter disagreement running alongside these larger ones, one that most people outside the field have never heard of, sometimes called the S8 tension. concerning how clumped together matter appears to be across the universe, when astronomers directly measure the actual clustering of matter in space, using surveys that track how the light from distant galaxies is subtly bent and distorted by the gravity of everything lying between them and us. They consistently find slightly less clumping than the Standard Model predicts there should be. Rees himself has described it, informally, as something like the little sibling of the larger expansion rate disagreement, less dramatic in scale, but persistent enough to be worth watching closely. And if both of these disagreements turn out to be pointing at something genuinely real, rather than statistical coincidence or overlooked error, they may ultimately turn out to be two separate cracks running through the very same underlying wall. None of this is the private concern of a handful of isolated researchers working alone. More than 500 scientists have come together into a single large collaboration, pooling their individual measurements and compiling an extensive shared document that catalogues each of these disagreements in detail, mapping out precisely where theory and observation currently refuse to align. It is a rare thing in any scientific field to see this scale of coordinated effort devoted to cataloging what is not yet understood, rather than what already is. And it says something about how seriously this collection of puzzles is being taken across the discipline as a whole. Meanwhile, the instruments involved keep growing more precise rather than less. A powerful telescope situated high in the Chilean desert, chosen for its thin, dry air and clear skies, recently produced the most detailed ground-based map ever made of that ancient afterglow of light left over from the early universe. Many researchers had hoped this new, sharper map might nudge the early universe expansion number upward, closer to the value measured through the distance ladder, quietly narrowing the gap between the two competing methods. It did nudge the number, slightly, but nowhere near enough to close the disagreement. The gap held, and then there is, perhaps, the deepest and most unsettling wrinkle of all, coming from an entirely different kind of instrument, one capable of gathering the light of 5,000 galaxies simultaneously, compiling the most ambitious three-dimensional map of the universe's structure ever attempted, reaching back across roughly 11 billion years of cosmic history. This instrument has begun to hint at something that would unsettle even the calmest working cosmologist. If it holds up under further scrutiny, it suggests that dark energy itself, the mysterious force responsible for roughly 70% of everything that exists, and the very thing driving the accelerating expansion of the universe, might not actually be constant over time. For roughly a quarter of a century, the working assumption among cosmologists has been that dark energy is a fixed, unchanging property of empty space itself, exactly as strong today as it was billions of years ago, and presumably just as strong billions of years from now. But when this enormous new galaxy map is combined with the ancient afterglow of light from the early universe, with distant exploding stars, and with the subtle bending of light by gravity across vast cosmic distances, the simplest explanation, the one where dark energy never changes, starts to look slightly less secure. The combined data leans, gently but noticeably, toward a version of dark energy that was somewhat stronger in the distant past and has been gradually weakening ever since. It is important to say clearly that this signal has not yet reached the very high level of statistical certainty that physicists typically demand before treating something as an established discovery, and a number of careful researchers have cautioned, quite reasonably, that it remains too early to state this as settled fact. But the implication, if it holds up under further observation, is genuinely significant. It would mean the underlying force shaping the ultimate fate of the universe is not a fixed constant at all, but something actively changing, even now, beneath everything we observe. and it would mean the Standard Model, built to describe that force, may eventually need meaningful revision. Consider, for a moment, where that possibility leads. For decades, the assumed ending to this particular story felt settled. A universe with constant, unchanging dark energy expands forever, faster and faster, until galaxies drift entirely beyond one another's reach. Stars burn through their fuel one by one over unimaginable stretches of time, and everything gradually fades into a cold, dark, and largely empty cosmos. It was not a cheerful ending, but at least it felt like a certain one. If dark energy is instead fading over time, that certainty softens considerably. An expansion driven by a weakening force could, in principle, eventually slow down or stall entirely. And in some of the more speculative versions of this idea, it could even reverse direction altogether, drawing the universe back together towards some kind of eventual collapse, unfolding over a timescale so distant it is difficult to even meaningfully compare to anything in human experience. We simply do not know which of these outcomes is correct, and that uncertainty is, in itself, the entire point. The long-term future of the universe, which many assumed had been quietly settled decades ago, has become an open question once again, despite everything gathered here. It is worth saying plainly that nobody serious in this field believes the Standard Model of Cosmology is somehow broken or on the verge of collapse. It is not even close to that. This same framework still explains the detailed properties of that ancient afterglow of light with extraordinary precision. It still correctly predicted the exact proportions of hydrogen and helium that make up the early universe, a calculation that has held up beautifully for decades. It still accounts for the way galaxies cluster together across the largest structures in the observable universe. No competing framework comes anywhere close to matching its overall track record. What has changed is that a handful of genuine fractures have opened up around the edges of that framework. Fractures that simply were not visible with the instruments available even a decade ago. It might help, at this point, to spend a little time on where the idea of dark matter itself actually came from, since it sits underneath so much of what we have been discussing. The story begins in the 1930s with an astronomer named Fritz Zwicky, who was studying a large cluster of galaxies and noticed that the individual galaxies within it were moving far too quickly to be held together by the gravity of the visible matter he could actually see. By his calculations, the cluster should have flown apart long ago, unless there was a great deal of additional, invisible mass holding it together gravitationally. At the time, this idea was met with considerable skepticism, and it remained a fairly obscure curiosity for decades. It was not until the 1970s, through the careful work of an astronomer named Vera Rubin, that the idea gained wider acceptance. Rubin studied the rotation of stars within spiral galaxies and found something that should not have been possible. If those galaxies contained only the mass visible in their stars and gas, stars far out at the edges of a galaxy's disk were orbiting just as fast as stars much closer to the center, when ordinary gravity, based only on visible matter, predicted they should be orbiting noticeably more slowly the farther out they were, the same way outer planets in our own solar system orbit the sun more slowly than inner ones. The only way to explain these unusually fast outer orbits was to assume each galaxy was embedded within a much larger, invisible halo of additional mass, extending well beyond the visible disk, exerting its own gravitational pull. That invisible mass came to be known as dark matter, and Rubin's careful observational work, repeated across dozens of galaxies, eventually turned it from a fringe curiosity into one of the pillars of modern cosmology. Understanding dark matter's history helps explain why the recent observations of unusually elongated, cigar-shaped early galaxies carry so much weight. Cold dark matter, the the specific version of the theory that has dominated cosmology for the past several decades, makes fairly precise predictions about how galaxies should be shaped as they first assemble. Predictions built up over many years of increasingly detailed computer simulations. If those predictions consistently fail to match what is actually observed, the disagreement does not stay contained to a small technical corner of astrophysics. It calls into question assumptions that touch nearly every other part of the standard cosmological framework, precisely because dark matter functions as such a foundational ingredient within it. It is also worth understanding, in a little more depth, exactly how researchers measure something as intangible as the clumping of matter across the universe, which is what the quieter S8 disagreement mentioned earlier is actually built upon. As light from extremely distant galaxies travels toward us across billions of light years, it passes through countless intervening clumps of matter, both visible and dark, and the gravity of that intervening matter subtly bends and distorts the light's path. In much the same way a lens bends light passing through it, this effect, called gravitational lensing, is usually far too subtle to notice by eye in any single galaxy. But by studying the shapes of millions of distant galaxies statistically, researchers can measure the average distortion and work backward to determine how much matter, and how densely clumped that matter is, lies along the path the light traveled. Several large sky surveys have carried out exactly this kind of measurement, and they consistently find slightly less clumping than the Standard Model predicts, a small but persistent gap that has resisted easy explanation for years now. There is a comforting, well-worn pattern in the history of physics, one that stretches back well beyond cosmology. Worth mentioning here because it puts the current situation into a gentler context. Physics has a long habit of running into small, stubborn discrepancies that eventually turn out to be doorways into entirely new understanding, rather than simple errors waiting to be corrected away. In the late 1800s, astronomers noticed that the planet Mercury's orbit around the Sun was behaving in a very slightly odd way. Its closest approach to the Sun was gradually shifting position over time, precessing, at a rate that Newton's centuries-old theory of gravity could not quite account for, no matter how carefully the calculation was checked. For decades, some astronomers proposed that an entirely undiscovered planet, sometimes nicknamed Vulcan, must be orbiting even closer to the Sun than Mercury, its gravity tugging on Mercury and causing the discrepancy. Extensive searches for this hypothetical planet turned up nothing. The mystery sat unresolved for the better part of half a century. The eventual resolution came not from finding a hidden planet, but from an entirely new theory of gravity itself. Einstein's general theory of relativity, developed in the early 1900s, described gravity not as a simple force acting between objects, but as the bending of space and time itself around massive objects. When the equations of this new theory were applied to Mercury's orbit, they predicted exactly the small extra precession that had puzzled astronomers for decades, without requiring any hidden planet at all. A minor, stubborn discrepancy in a well-established theory turned out to be an early clue pointing toward one of the most significant scientific revolutions of the 20th century. A similar pattern appeared around the same period in a completely different branch of physics. Late in the 1800s, physicists studying how hot objects radiate energy found that their best existing theory made an absurd prediction, that a hot object should radiate an essentially infinite amount of energy at very short wavelengths of light. A prediction so clearly wrong that physicists at the time only half-jokingly referred to it as the ultraviolet catastrophe. The resolution, worked out gradually by physicists, including Max Planck, the same physicist the modern satellite mission was later named after, required assuming that energy could only be absorbed or emitted in small, discrete packets. rather than smoothly and continuously as classical physics had always assumed. That single assumption, adopted somewhat reluctantly at first as a mathematical trick to fix an obviously broken prediction, turned out to be the opening chapter of an entirely new branch of physics, the one we now call quantum mechanics, which has since reshaped our understanding of nearly everything at the smallest scales of nature. Both of these historical episodes share a common shape with the situation cosmologists currently find themselves in. A small, stubborn discrepancy appears between careful theory and careful observation. Initial attempts to explain it away as a simple error or an overlooked technical detail fail, sometimes for decades, and eventually the discrepancy resolves not by patching the old theory, but by revealing something genuinely new about how nature works, something nobody had previously had any particular reason to suspect. Whether the modern disagreements over the universe's expansion rate, the shapes of early galaxies, or the possible evolution of dark energy will follow this same pattern remains to be seen. But the historical precedent offers a useful, steadying kind of perspective. Crises like this one have a track record, in physics, of turning out to be doors rather than dead ends, and there are, already, several new instruments being built and launched specifically to push on these doors and see what lies beyond them. A new space telescope, designed specifically to survey enormous swaths of sky in search of clues about dark energy, is currently being prepared for launch. Rather than focusing narrowly on individual galaxies the way earlier telescopes have, it is built to survey huge areas of the sky at once, tracking how billions of galaxies are distributed and how that distribution has changed across cosmic history, gathering exactly the kind of large-scale statistical data needed to determine whether dark energy truly is evolving over time or whether it has been constant all along. A separate mission, launched by the European Space Agency, is already in the process of charting the precise shapes, positions, and distances of billions of galaxies, constructing what is sometimes described as a map of the invisible scaffolding of the universe, the underlying distribution of dark matter that ordinary visible galaxies trace out, on a scale and level of detail never attempted before. Its results, expected over the coming years, should offer an independent check on many of the puzzles described here, from the shapes of early galaxies to the clumping measurements behind the S8 disagreement and a dedicated satellite mission is steadily improving our knowledge of the precise distances to nearby stars, including many of the pulsing stars that anchor the bottom rung of the cosmic distance ladder, using a technique called parallax, which measures the tiny apparent shift in a star's position as the Earth orbits the Sun, essentially the same principle behind depth perception in human vision, just applied with extraordinary geometric precision across the galaxy. As that satellite's catalogue of stellar distances continues to improve, it strips away one of the last remaining places where a subtle, hidden error could still be lurking in the foundation of the distance ladder. It might help, at this point, to slow down and look more closely at the physics behind those exploding stars used in the distance ladder, since their remarkable consistency is what makes the whole method work in the first place. These particular explosions come from a type of dead star called a white dwarf, the small, extremely dense remnant left behind after a sun-like star has exhausted its nuclear fuel and shed its outer layers. A white dwarf on its own is stable, slowly cooling over billions of years without further incident. But if that white dwarf happens to be orbiting closely with a companion star, it can gradually pull material from that companion onto itself, growing steadily heavier over time. There exists a very specific mass limit, worked out through careful physics calculations and named after the astrophysicist who first derived it, beyond which a white dwarf simply cannot remain stable. As the white dwarf's mass approaches this limit, gathering material from its companion, it eventually crosses a threshold where its internal pressure can no longer support it against its own gravity, triggering a runaway nuclear reaction that tears the entire star apart in a matter of seconds, releasing an almost unimaginable amount of energy in the process. Because nearly every white dwarf that explodes this way does so at almost exactly the same critical mass. The resulting explosions release almost exactly the same amount of energy every time, regardless of which galaxy or which era of cosmic history they occur in. That consistency is precisely what makes them useful as what astronomers call standard candles, objects whose true brightness is reliably known in advance, allowing their observed faintness to be translated directly into a distance, no matter how far away they are. It is a beautiful example of how a fairly obscure and specific piece of stellar physics, worked out through careful theoretical calculation, ends up underpinning one of the most important observational tools in all of cosmology. It is worth being equally careful about the physics behind the other end of the distance ladder, the ancient afterglow of light from the early universe. Since a related concept called baryon acoustic oscillations plays an important role both in interpreting that early light and in some of the newer galaxy mapping efforts mentioned earlier. In the hot, dense plasma of the very early universe, ordinary matter and light were tightly coupled together, pushing and pulling against each other in a way that set up genuine sound waves, ripples of compression and rarefaction moving outward through the cosmic plasma, not unlike sound waves moving through air, just on an almost inconceivably vast scale. These sound waves continued rippling outward until the moment the universe became transparent, at which point they were essentially frozen in place, leaving behind a subtle, consistent pattern in how matter is distributed across the universe. A very slight tendency for galaxies to be found at one particular characteristic separation from each other, more often than at other distances, because the physics governing the size of these frozen sound waves is well understood and precisely calculable. That characteristic separation distance functions as another kind of standard ruler, one that shows up both in the ancient afterglow of light and, much later in cosmic history, in the actual distribution of galaxies across the sky, measuring how that characteristic separation appears at different points across cosmic history is exactly the technique used by the instrument capable of mapping 5,000 galaxies at once. And it is precisely this technique that has produced the recent, still preliminary hints that dark energy may be evolving over time rather than remaining constant, returning to the puzzle of unexpectedly massive early galaxies. It helps to have a clearer sense of the broader timeline those galaxies are being measured against, since the surprise only really makes sense once you understand roughly what was supposed to happen and when. For the first few 100 million years after the universe became transparent, there were no stars or galaxies at all, just a vast, dark expanse of mostly hydrogen and helium gas, gradually being pulled together by the gravity of dark matter into larger and larger clumps. Astronomers sometimes refer to this stretch of time as the cosmic dark ages, a period with no light sources of its own, illuminated only faintly by the fading afterglow of the Big Bang. Eventually, within the densest of these gathering clumps of gas, conditions grew extreme enough for nuclear fusion to ignite, and the very first generation of stars flickered on, thought to have been unusually massive and short-lived compared to typical stars today, burning through their fuel quickly and ending their lives in dramatic explosions that seeded the surrounding gas with the first heavier elements ever to exist. The light from these earliest stars gradually stripped electrons back off the surrounding hydrogen atoms in a process called transforming the universe from a mostly neutral, dark expanse into the ionized, transparent state that mostly persists throughout the universe today. This entire process, from the first stars flickering on to the completion of reality, is generally thought to have unfolded over several 100 million years, gradually building up the first small, irregular galaxies from countless individual clusters of these early stars merging and growing together over time. Only gradually, over the following billions of years, did small early galaxies merge and grow into the larger, more organized structures familiar today, including full spiral galaxies like our own, with their smooth, orderly rotating disks. This gradual, patient buildup is precisely what makes the newly discovered massive early galaxies so surprising. They appear to have compressed a growth process that was expected to take many billions of years into a small fraction of that time, which is why researchers describe them as pressing right up against the theoretical limits of what current models allow. The compact, intensely red, black hole-powered objects mentioned earlier, the ones that turned out to be responsible for inflating the apparent mass of some early galaxies, have become a research topic in their own right, sometimes informally nicknamed little red dots by the astronomers studying them, owing to their small apparent size and distinctly reddish color in the telescope's images. Their exact nature is still being actively debated. Some researchers believe they represent an early, especially active phase of supermassive black hole growth, feeding unusually quickly on surrounding gas before settling into a calmer state later in cosmic history. Others suspect at least some of them may be a genuinely new category of object, not quite matching either the feeding black holes or the massive galaxies previously catalogued in the nearby, more easily studied universe. Sorting out exactly what these objects are, and how many of the previously reported overweight early galaxies they might still be quietly inflating, remains an active and genuinely open area of research. It is worth spending a little more time on the alternative dark matter ideas mentioned earlier, the ones that seem to fit the unusually elongated shapes of some early galaxies a bit more comfortably than the standard cold, dark matter picture does. For most of the past several decades, the leading candidates for what dark matter actually is have been hypothetical particles that are heavy, slow-moving, and interact with ordinary matter only through gravity and possibly one other very weak force. These particles are often referred to, somewhat awkwardly, by an acronym describing them as weakly interacting and massive. Enormous, sensitive detectors have been built deep underground, shielded from cosmic radiation, specifically to try to catch one of these particles interacting, however rarely, with ordinary matter. So far, despite decades of increasingly sensitive searches, none have been conclusively detected, which has led some researchers to widen their thinking toward other possibilities. One such alternative proposes that dark matter might instead be made of particles that are extraordinarily light, so light that they behave less like discrete individual particles and more like a smooth, wave-like fluid spread out across space, governed by the same strange rules of quantum mechanics that govern the behavior of subatomic particles, just stretched out to a scale where those wave-like properties become noticeable across distances comparable to entire galaxies. This idea is sometimes called wave dark matter or fuzzy dark matter, and one of its more distinctive predictions is that it should smooth out and suppress the formation of very small-scale structures in the early universe, while still allowing larger structures like galaxies to form in a somewhat different, less densely clumped way than standard cold dark matter would predict, potentially helping to account for the unusual elongated shapes observed in some of these early galaxies. Related but distinct family of ideas proposes that dark matter particles might simply be somewhat warmer, in a technical physics sense, meaning they retain more residual motion from the early universe than the standard cold, dark matter picture assumes, which would also tend to smooth out small-scale clumping in a way that could plausibly explain some of the same observed features. Both of these alternative families of ideas remain genuinely speculative and are actively debated within the research community, and it is worth emphasizing that no consensus currently exists favoring them over the standard cold, dark matter picture. What has changed is that observations from the newest telescope have given researchers enough new data about the shapes of very early galaxies to start meaningfully testing these alternative ideas against reality for the first time. Rather than treating them purely as mathematical curiosities, it might be worth pausing here to say something about how scientists think about disagreements like these in general. Since the word tension can sound more alarming than it is actually meant to be, in careful precision science, almost every measurement comes with what is called an uncertainty, a stated range within which the true value is expected to fall, based on a careful accounting of every known source of possible error, statistical noise, and instrumental limitation. When two independent measurements of the same quantity produce values that do not overlap within their stated uncertainties, that is what scientists mean when they describe a tension. It does not automatically mean either measurement is wrong. It means that at least one of two things must be true. Either there is some subtle, not yet identified source of error in one or both measurements, quietly inflating or deflating the number without anyone realizing it, or the two measurements are correctly capturing two genuinely different physical realities, which would mean the simple theoretical framework connecting them together is somehow incomplete. History offers examples of both outcomes. There have been well-known cases where an apparent tension between two important measurements eventually traced back to a subtle, instrumental error. One memorable example from a completely different area of physics involved an experiment that appeared, for a brief period, to show subatomic particles called neutrinos traveling very slightly faster than the speed of light, a result that would have overturned a foundational pillar of modern physics if it had held up. The scientific community responded with appropriate caution rather than panic. Other experiments were quickly organized to check the result, and eventually a loose, faulty cable connection within the original experiment's timing equipment was identified as the culprit, fully explaining the anomalous measurement without requiring any change to our understanding of the speed of light. That example is sometimes cited as a cautionary tale about jumping to dramatic conclusions too quickly. But the earlier story about the accelerating expansion of the universe and the age of the oldest stars is an equally well-known example of the opposite outcome, where a persistent tension turned out to reflect something genuinely new about nature, rather than a hidden error waiting to be found. Distinguishing between these two possibilities in real time, while the evidence is still incomplete, is genuinely difficult. And it is precisely why so many careful researchers continue to test and retest the current cosmological disagreements from as many independent angles as possible. Rather than declaring victory or defeat prematurely in either direction, it is worth returning briefly to Wendy Friedman's independent measurement technique, since understanding it a little more deeply helps explain why her result carries genuine weight rather than simply representing a dissenting opinion. Her method relies on a different category of aging star, one found in the outer sparser regions of galaxies, stars nearing the end of a particular stage of their evolution, a phase where their brightness climbs steadily as they age until reaching a sudden, sharp, and remarkably consistent peak brightness, at which point their internal structure abruptly changes and their brightness drops again. That sharp, well-defined peak, often referred to informally as the tip of a particular branch on a diagram astronomers use to chart stellar evolution functions as another kind of standard candle, similar in spirit to the pulsing stars used in the more traditional distance ladder, but relying on an entirely different underlying stellar physics, and crucially found in far less crowded regions of their host galaxies, which sidesteps the exact blurring concern that motivated so much of the original skepticism toward the higher expansion rate measurement in the first place. That her method, built on entirely different physical stars and entirely different regions of each galaxy, converges on a number sitting comfortably between the two competing camps, is precisely what makes her result so difficult for either side to simply dismiss. It is worth taking a moment to appreciate the telescope itself a little more fully, since so much of this story depends on its particular capabilities, rather than orbiting the Earth closely. The way its predecessor did, this newer observatory sits at a special, gravitationally stable location roughly 1.5 million kilometers away, on the side of the Earth facing away from the Sun, a location where the combined gravity of the Earth and Sun allows a spacecraft to maintain a fairly stable position with only minimal fuel expenditure over time. From this distant vantage point, a large, 5-layer sunshield, roughly the size of a tennis court, shields its sensitive instruments from the light and heat of both the Sun and the Earth, allowing the telescope's mirrors and detectors to cool down to extremely low temperatures, just a few tens of degrees above absolute zero. This extreme cold is essential because the telescope is designed primarily to observe infrared light, and any warmth in the telescope's own structure would otherwise flood its detectors with its own thermal glow, drowning out the faint infrared signals arriving from distant galaxies. Its primary mirror, rather than being a single solid piece of glass, is built from 18 individual hexagonal segments, each coated in an extremely thin layer of gold, chosen because gold reflects infrared light with exceptional efficiency. These segments were folded up for launch and had to unfold with extraordinary precision once in space, a process involving hundreds of individual mechanisms that all had to work correctly, since there was no possibility of a repair mission at such a distant location. The successful unfolding of this mirror and the successful deployment of the sunshield are widely regarded among engineers as one of the most technically demanding spacecraft deployments ever attempted. Once operational, the telescope's suite of instruments allows it to do several different kinds of science simultaneously, from capturing detailed images of individual galaxies to splitting incoming light into its component wavelengths, a technique called spectroscopy, which allows astronomers to determine not just how far away and how bright a distant object is, but also its chemical composition, its temperature, and in many cases, the rate at which it is forming new stars. It is this combination of extreme sensitivity, careful cooling, and versatile instrumentation that has allowed it to gather the kind of decisive data on distant pulsing stars and ancient galaxies described throughout this account. The earlier satellite that mapped the ancient afterglow of light from the Big Bang operated on rather different principles, though it shared the same fundamental need for extreme cold and careful shielding from interference. Rather than forming detailed images the way the newer telescope does, it was designed to measure extremely subtle temperature variations across the entire sky, differences smaller than a millionth of a degree, in the faint microwave glow left over from the early universe. It carried out this work from a similar gravitationally stable location, slowly scanning the entire sky over and over across several years of operation, gradually building up an extraordinarily precise map, sensitive enough to reveal the tiny density fluctuations that would eventually grow over billions of years into the great cosmic structures of galaxies and galaxy clusters we observe today. The mission concluded its primary observations after several years, but its final, fully processed data continues to serve as one of the most important reference points in all of modern cosmology, the baseline against which so many of the tensions described here are ultimately measured. That there is another observatory worth mentioning here, one named in honor of the same Vera Rubin whose careful measurements of galaxy rotation first helped establish dark matter as a serious scientific idea rather than a fringe curiosity. This newer observatory, built on a mountaintop in Chile, is equipped with the largest digital camera ever constructed for astronomical use, and its primary mission is to repeatedly photograph the entire visible night sky, over and over, every few nights, for a full decade, rather than staring intently at one small patch of sky the way many telescopes do. It is designed to notice change, anything that moves, brightens, dims, or explodes across an enormous portion of the sky, compiled into what will eventually become the largest catalogue of astronomical objects ever assembled. Among its many scientific goals, it is expected to catalogue enormous numbers of distant exploding stars useful for the distance ladder, and to map the distribution of galaxies across a large fraction of the observable universe, offering yet another independent line of evidence bearing on both the expansion rate disagreement and the clumping measurements behind the quieter S8 tension. It is worth pausing, too, on how these various puzzles connect to a broader, more human question, one a little removed from the technical details of expansion rates and galaxy shapes. If the age of the universe, or the precise timeline of when the first stars and heavier elements formed, shifts even modestly as these tensions get resolved one way or another, it subtly reshapes our understanding of how much cosmic time has actually been available for complex chemistry, and eventually biology, to arise anywhere at all. This is not a dramatic or immediate concern, since even the largest currently proposed shifts amount to hundreds of millions of years out of a total cosmic history measured in the billions. But it is a genuine reminder that questions which sound purely abstract, confined to charts and equations, ultimately connect back to much larger questions about our own origins and how common or rare the conditions for life might be across the universe. It is worth being careful here not to overstate any of this. None of the observations described throughout this account suggest that the fundamental picture of a universe, roughly 14 billion years old, born from an incredibly hot, dense early state, and gradually cooling and structuring itself into galaxies, stars, and eventually planets, is in any serious doubt. The disagreements involved are refinements at the edges of an otherwise remarkably successful theory, not challenges to its basic outline. Framing them otherwise would be its own kind of inaccuracy, trading a genuinely interesting scientific story for an artificially dramatic one. That said, the accumulation of these specific, well-measured puzzles, the persistent expansion rate disagreement, the surprisingly massive and surprisingly shaped early galaxies, the quieter clumping tension, and the tentative hints of an evolving dark energy, does suggest that the coming decade of cosmology is likely to look meaningfully different from the one before it, whichever combination of explanations eventually proves correct. Whether some version of early dark energy, some revision to our understanding of dark matter, previously unaccounted for instrumental effects, or some genuinely new piece of physics nobody has yet proposed, the resolution is likely to teach cosmologists something they did not previously know. In much the same way earlier crises in the history of physics eventually did, there is a third, still developing method for measuring the universe's expansion rate that deserves mention here, since it comes from an entirely different branch of astronomy and offers a genuinely independent check on the two older techniques described earlier. When two extremely dense collapsed stars called neutron stars, spiral into each other and eventually collide. The collision briefly warps the fabric of space and time itself, strongly enough to send ripples outward that can, in principle, be detected here on Earth using extraordinarily sensitive instruments built specifically to measure these ripples in space. These instruments work by bouncing laser light down two long, perpendicular tunnels and measuring, with almost unbelievable precision, whether the tunnels have very slightly changed length relative to each other as a passing ripple stretches space in one direction while compressing it in the other. What makes these particular collisions useful for measuring the expansion, the rate of the universe, is that the pattern of ripples they produce directly encodes the true distance to the collision, without needing to rely on any of the calibration steps involved in either the pulsing star distance ladder or the ancient afterglow of light. If astronomers can also identify a burst of ordinary light accompanying the collision, which happened for one such event observed some years ago, they can measure how much that light has been stretched by the expansion of the universe during its journey to Earth, and combine that with the independently measured distance from the space-time ripples themselves to calculate the expansion rate directly, through an entirely different chain of physics than either of the two older methods relies upon. This technique, sometimes informally described as using these collisions as standard sirens, in a loose echo of the standard candle terminology used for exploding stars, is still limited by how rare these detectable collisions are and by the practical difficulty of also catching the accompanying burst of ordinary light. So far, the handful of events measured this way have not been numerous or precise enough to definitively favor one side of the expansion rate disagreement over the other, though the individual measurements obtained so far have tended to fall in a broad range compatible with both competing values. As detection instruments continue to improve in sensitivity over the coming years, and as more of these rare collisional events are hopefully caught with an accompanying light signal, this method holds real promise as a genuinely independent tiebreaker, one built on entirely different physics than either of the two methods currently locked in disagreement. It is worth also saying a little more about how the instrument capable of gathering light from 5,000 galaxies simultaneously actually accomplishes that feat, since the engineering involved is itself a small marvel. Rather than pointing a single set of optics at one target at a time, this instrument uses thousands of small robotic positioners, each one able to swivel independently and precisely align a thin optical fiber onto the exact position of a single distant galaxy, all coordinated together so that thousands of individual fibers can each be gathering the light of a separate, specific galaxy at the very same moment. This dramatically speeds up the process of gathering the kind of detailed spectroscopic data, revealing both distance and detailed physical properties that would otherwise take an impossibly long time to collect one galaxy at a time, allowing the survey to build its enormous 3D map of millions of galaxies across a scientifically practical time frame. The new Space Telescope mentioned earlier is named in honor of Nancy Grace Roman, an astronomer who served as NASA's first chief of astronomy and who played a foundational role in establishing the original Hubble Space Telescope program decades before that telescope ever launched. Fittingly, this newer mission carries her name into the next generation of cosmological survey work. Its wide field of view, roughly 100 times larger than that of the Hubble Space Telescope, while maintaining comparably sharp image quality, will allow it to survey enormous areas of sky in a single observation, rather than the comparatively narrow, deep views that earlier space telescopes have specialized in. Among its planned surveys is an approach that searches for extremely brief, subtle brightening events caused when a foreground object, sometimes an entire galaxy's worth of dark matter, sometimes a single rogue planet drifting unattached to any star, happens to pass almost exactly between Earth and a more distant background star, its gravity briefly acting like a lens and magnifying the background star's light in a distinctive, measurable pattern. Cataloging enormous numbers of these events across the crowded central region of our own galaxy offers another, indirect but genuinely independent way to study the distribution and possible nature of dark matter, complementing the galaxy shape measurements that have proven so puzzling in the very distant early universe. Taken together, these various instruments, the newest infrared space telescope with its sharp vision, the ground-based array mapping 5,000 galaxies at once, the ambitious European mission charting billions of galaxy shapes, the wide-field successor telescope named for Nancy Grace Roman, the enormous 10-year survey underway at the observatory named for Vera Rubin, and the ongoing, gradually improving effort to catch space-time ripples from colliding neutron stars represent an extraordinarily broad, multi-pronged effort to attack these open questions from as many independent directions as possible. It is genuinely rare in the history of science to see this many different techniques built on this many different branches of physics, all converging on the same handful of open questions at roughly the same moment. Whatever the resolution eventually turns out to be, it seems very unlikely to come from any single measurement in isolation. It will more likely emerge gradually from the patient cross-checked agreement or persistent disagreement. Among all of these different approaches taken together, it is worth also saying something about how results like these actually spread through the scientific community and get tested by other researchers, since the process is a little different from how discoveries sometimes get portrayed. When a team completes a major measurement, whether it is Reese's group refining the distance ladder or the collaboration behind the 5,000 Galaxy survey, reporting hints of evolving dark energy, the first step is typically to post a detailed paper describing the methods and results on a shared online repository, making it available to other researchers around the world well before it appears in a formal, peer-reviewed journal. Other scientists then pore over the methodology, checking for overlooked sources of error, attempting to reproduce the analysis using the same publicly available data, and often publishing their own follow-up papers, either supporting, questioning, or refining the original conclusions. This is precisely the process that led to the careful re-examination of the apparently overweight early galaxies, revealing the black hole imposters hiding among them. It is the same process currently underway in response to the tentative hints of evolving dark energy, with numerous independent research groups currently working through the same underlying data using different analysis techniques, checking whether the same conclusion holds up regardless of the specific statistical choices made along the way. This ongoing, distributed, somewhat argumentative process of checking and rechecking is not a sign that something is wrong with the science. It is in fact exactly how reliable scientific consensus is supposed to be built, slowly, through repeated independent verification, rather than through any single announcement being accepted immediately at face value. It is precisely because of this careful, distributed checking process that the expansion rate disagreement has remained so persistently unresolved for as long as it has. If it were the result of some simple, easily identifiable error, the enormous number of careful researchers examining every detail of both competing methods over more than a decade would very likely have already found it. Its persistence, despite this intense and sustained scrutiny, is itself part of why so many cosmologists now suspect that something genuinely new about the universe may be hiding within it. So where does all of this actually leave things? At this particular moment in the story, the disagreement over the universe's expansion rate remains genuinely unresolved. The distance ladder built from pulsing stars and exploding stars continues to produce a value close to 73.5. The extrapolation forward from the ancient afterglow of light continues to produce a value close to 6. Wendy Friedman's independent method continues to sit closer to 70, comfortably compatible with the lower value and only mildly in tension with the higher one. Early dark energy remains an elegant but entirely undetected candidate explanation. The recently proposed idea involving primordial magnetic fields remains speculative and freshly published, its implications not yet fully worked through. Nobody currently knows, with real confidence, which of these explanations, if any, is correct, or whether the true answer involves some combination of several of them together, or something else entirely that nobody has proposed yet. The question of unusually massive, unusually early, and unusually shaped galaxies remains similarly open. Removing the black hole imposters resolved much, though not all, of the original surprise, leaving a smaller but still meaningful excess of massive early galaxies still unaccounted for. The coexistence of chaotic, still-forming galaxies, alongside at least one fully organized early spiral, within the very same window of cosmic time, remains a puzzle without a fully satisfying explanation. The unusually elongated shapes observed in a number of early galaxies remain a genuinely contested area, with researchers still actively debating whether they point towards some revision of dark matter physics, or whether some more mundane explanation involving how these very distant, faint objects are observed and measured will eventually account for them instead. The quieter S8 tension concerning the overall clumpiness of matter across the universe remains persistent, smaller in magnitude than the expansion rate disagreement, but stubbornly present across multiple independent surveys, and its ultimate relationship to the other puzzles described here, whether it is a symptom of the same underlying cause or an entirely separate issue, remains unclear, and the tentative hint that dark energy itself might be evolving over cosmic time, rather than remaining perfectly constant, remains just that, a hint, not yet confirmed to the level of certainty that would allow physicists to treat it as an established fact, though a genuinely intriguing one that a great deal of current and upcoming observational effort is specifically designed to test more rigorously. What is happening right now, in real time, is an unusually large and unusually well-coordinated effort to attack all of these open questions simultaneously, using instruments built on entirely different physical principles, specifically so that any eventual resolution can be checked and cross-checked from as many independent angles as possible, minimizing the chance that some hidden, shared source of error is quietly responsible for multiple puzzles at once. Over the coming several years, the Wide-Field Successor Telescope, named for Nancy Grace Roman, is expected to begin its survey work. The European mission, charting billions of galaxy shapes, is continuing to release new results. The observatory named for Vera Rubin is now steadily compiling its decade-long survey of the changing night sky, and the instrument capable of gathering light from 5,000 galaxies at once continues to release increasingly precise results from its ongoing survey, each new data release offering another opportunity to either strengthen or weaken the tentative hint of evolving dark energy first suggested by its earlier results. It is genuinely difficult to predict, from where things currently stand, exactly how any of this will resolve. That, ultimately, is precisely what makes this such a genuinely interesting moment in the history of cosmology, rather than a settled or closed one. For the better part of a century, our basic picture of the universe, its age, its origin, its overall composition and behavior has grown steadily more precise and more confidently established. one careful measurement layered on top of another. What has changed only in the past few years is that our instruments have finally become sharp enough to notice small, genuine cracks running through the edges of that otherwise remarkably successful picture. Cracks that were simply invisible to any earlier generation of telescopes. Whether those cracks eventually get patched over by some overlooked technical correction, or whether they turn out the way similar cracks have at least twice before in the history of physics, to be the first visible edge of something genuinely new about how the universe works, is a question that current instruments are only just now becoming powerful enough to properly investigate. Nobody currently knows the answer. For now, the most honest thing that can be said is that a great many careful, patient people are looking very closely, checking each other's work, building new instruments specifically designed to settle the matter, and slowly, methodically, narrowing down the possibilities, the same unhurried way careful science has always worked. One confirmed measurement, one ruled-out explanation, one small piece of the picture at a time. The universe, as far as anyone can currently tell, is not broken. It is only that our map of it, drawn with tremendous care over the better part of a century, has recently revealed a few regions where the edges do not quite line up the way earlier cruder maps once suggested they would. That is not a small thing, and it is not a cause for alarm either. It is simply where the frontier of this particular science happens to sit right now, and frontiers, in physics, have a long and fairly reassuring habit of eventually leading somewhere worth arriving at. It is worth noting, too, just how international and how collaborative this entire effort has become. The team behind the pulsing star distance ladder includes researchers spread across universities on several continents. The 500 scientists consortium cataloging these various tensions draws its members from national laboratories, universities, and space agencies across North America, Europe, and Asia. The instrument mapping 5,000 galaxies at once is operated by a collaboration spanning dozens of institutions worldwide, sharing both the enormous cost of building such a facility and the enormous volume of data it produces. Modern cosmology, in this sense, looks less like the work of any single brilliant individual working alone, the way the field is sometimes still imagined, and much more like an unusually large, patient, quietly cooperative undertaking, spread across thousands of careful people, each contributing one small, well-checked piece to a picture none of them could possibly complete alone. It is a slower, quieter kind of story than the one sometimes told about scientific discovery, without a single dramatic eureka moment or a lone genius suddenly seeing what nobody else could. It is built instead from thousands of careful, unglamorous choices: which telescope to point where, which star to measure again for the third or fourth time, which small correction to apply and which to leave out, repeated patiently across years and continents until, very gradually, a clearer picture starts to emerge from all that accumulated care. That patience seems, in the end, like the right note to sit with. Careful measurement, however precise, is rarely dramatic in the moment it happens. It looks like long nights spent gathering faint light, long months spent checking a calculation for a subtle, easily overlooked error, and long years spent waiting for the next generation of instruments to finally have the sensitivity needed to settle a question that has quietly lingered for a decade or more. The universe, whatever it ultimately turns out to be doing with its own expansion, does not appear to be in any particular hurry to reveal the answer. And so, for now, neither are the people carefully studying it. If this kind of quiet, unresolved mystery is the sort of thing that helps a mind settle rather than race, there is a great deal more of it out there, in cosmology and in almost every other corner of science, patiently waiting for someone curious enough to sit with it for a while. For now, though it is enough to simply picture it. A golden mirror, drifting slowly and quietly through the dark, 1.5 million kilometers from a small, wet, rocky planet, patiently gathering light that began its journey billions of years ago, still listening for whatever the universe has left to tell us. In no particular hurry to hear the rest of the answer tonight.